What is an Archimedean solid? An Archimedean solid is a special type of 3D shape or polyhedrons made from regular polygons like triangles, squares, or pentagons, arranged in a very balanced and symmetrical way. It is named after the ancient Greek mathematician named Archimedes. To identify an Archimedean solid, it must satisfy all of this. The first one is all faces are regular polygons. Means a regular polygon is a shape where all sides are equal and all angles are equal. For example, equilateral triangles, square, or regular pentagons. This means no irregular shapes allowed, and every faces must be perfectly uniform. The second one is it uses more than one type of polygons. This is what makes Archimedean solids different from Platonic solids. Platonic solids only use one type of face. For example, cube equal to all squares. And Archimedean solids mix of faces. For example, the mix of triangles and squares. So, Archimedean solids are more complex but still orderly. The third one is same arrangements at every vertex. This is the most important rule. At every corners of our vertex, the same types of polygon meets in the same order. For example, if at one vertex you see triangle, square, and then a square, then at every vertex it must be triangle, square, and square. No exception. This property is called vertex transitivity. The fourth one is the shape must be convex. Convex means no dents or inward curves and the shape bulges outwards. If you draw a line between any 2 points inside the shapes, the lines stay inside. So, no halo or star-like shapes and everything is a solid outward. Simple real-life examples is a soccer ball. It is actually a truncated icosahedron made of pentagons.
So, for the explanation, I'll be talking about faces, edges, and vertices. These are the net template for truncated tetrahedron. First of all, let's look at the edges. There are 12 edges that can be counted in this Archimedean. 1, 2, and 3 faces, and big fourth face, and adds up to 4 more faces, and there are 8 faces that can be found. Lastly, let's look at the vertical. There are 18 vertices in this Archimedean.
Okay, in this section, I will justify the geometric properties of the truncated tetrahedron using its net. The net allows us to clearly visualize how a two-dimensional layout forms a three-dimensional solid. Let me explain about these basic properties of the truncated tetrahedron. This solid consists of 8 faces, which include 4 hexagonal faces and 4 triangular faces. And it also has 18 edges and 12 vertices. We can tell that these values can be confirmed by carefully analyzing the net. Further justify this, we can apply Euler's formula, which states that vertices minus edges plus faces equals to 2, or we can say in simple V minus E plus F equals to 2. So substituting the values, we get 12 minus 8 plus 8 equals to 2. You can see that this satisfies Euler's formula. Next, we justify the surface area using the net. Since there are 4 hexagons and 4 triangles, the total surface area is obtained by summing the area of all these faces. Therefore, the surface area is equal to the total area of 4 hexagonal faces plus 4 triangular faces. This shows that the net provides a direct and logical way to calculate surface area. Volume of truncated tetrahedron represents the amount of space enclosed within the solid. Although the net itself is two-dimensional, it helps us to understand how the faces are connected to form a closed 3D-dimensional structure. Once the net is folded into the solid, the enclosed space forms the volume, which depends on the dimensions and arrangement of the faces. Why this net forms the solid? The net forms a truncated tetrahedron because the faces are arranged in a geometrically correct way. Each hexagon is connected to triangles and other hexagons along matching edges, allowing the faces to fold neatly into place. When folded, all faces meet perfectly without any gaps or overlaps. This shows that the structure satisfies the geometric conditions required to form a closed 3-dimensional solid. Some nets do not work. However, not all arrangement of these faces will form a truncated tetrahedron. Imagine if the hexagons and triangle are placed incorrectly. The faces may overlap or fail to connect properly when folded. For example, if too many faces meet at one vertex or if edges do not match in length, the solid cannot be formed. Thus, this demonstrates that a valid net must follow strict geometric rules, including correct edge alignment and proper angle relationships.
In conclusion, this project has helped us gain a clearer understanding of Archimedean solid, particularly the truncated tetrahedron, through both its construction and its nets. By constructing the nets, we were able to observe how the faces, edges, and vertices are arranged and how they connect to form a complete 3-dimensional structure. This made it easier for us to understand the relationship between a 2D net and its 3D solid form. We also verified that a correct net must be able to fold into a solid without any gaps, overlaps, or mismatched faces. This shows the importance of accuracy and spatial visualizations when working with geometric construction.